At the end of the day, excuse me, using this resistance network, we could write the flux equal to the change in concentration over the total resistance. So you had a change in concentration, you had a fraction going from 1 to 0, and you figured out what the total resistance was because you knew the length and you knew the diffusion coefficients for these materials. And you got an answer of about 7. Yes, sir.
How does the resistance, the mass resistance,
Yeah, so this mass resistance, if you look over at the exam, we looked at a form of Fick's law. So we took Fick's first law. This is going to be applied for stationary coordinates. And I think we assume a dilute solution. That would make sense in this case. There shouldn't be a high concentration of helium in the actual glass. So if we assume a dilute solution and we have a stationary coordinate system, we have Fick's first law. So we took Fick's first law, which would say that the molar flow of A is the flux of A times the surface area is equal to negative the total concentration of the system, the diffusivity of A through material B, times that surface area, times our driving force. In fact, if we have the concentration outside, this will be dxa, and let's have this be dy, so we don't have too many x's floating around in here. So we looked at Fick's first law, stationary coordinates, dilute system, and we integrated this. We just basically took MA and integrated this whole thing with Dirichlet boundary conditions. So we said if we have known concentrations and we have known distances that separate these concentrations, then I can rewrite this as the flux times some sort of length that I integrated over equal to DAB, the diffusion coefficient, times the surface area. And in this system, we assume total constant concentration. And in that case, we can bring the concentration in and out of the derivative. If we have the fraction of A times the total concentration, we can write that as the concentration of A. And we basically took this, solved it for the driving force over the resistance. So actually this wouldn't, because we integrated this over a length scale, so this is going to be delta C, and then we brought the y over here and changed it. So we'll have NA times L, negative DAB, AS, delta C. That's actually what we would have gotten, because we'd have separated this. dy goes over here, we integrate it, dx is on this side, we integrate it. And so solving this for Na is equal to, the concentration is our driving force, so we divide over by L. So this is 1 over the resistance, because it's multiplying by C, and we need C over the resistance. And so that's our resistance, L over dA. And I think most of you, including yourself, did really well on this, and you were able to get that during the exam.
Yeah.
So this negative, we actually, when we do a resistance network, We don't look at this as state 2 minus state 1. We look at it as a flow through a system. So we typically we reverse that delta in resistance networks. Yeah, if you think back to how you've looked at these resistance networks and how we've learned them, we always take state 1 minus state 2. Yeah, we reverse it. That's very astute. Good observation.